The Amazon rainforest covers 5.5 million square kilometers. It holds roughly 390 billion trees and 1 in 10 species on Earth. We call it the lungs of the planet, a phrase that suggests permanence, something ancient, unchanging, essential. But the Amazon as we know it is only 66 million years old. Before that, the same patch of ground held a completely different forest with opposite rules. The modern jungle, dense, dark, vertically layered, exists because an asteroid reset the entire system. The catastrophe that killed the dinosaurs created the rainforest. 66 million years ago, in what is now the Amazon basin, the forest was bright. Sunlight reached the ground. Trees stood spaced apart like pillars in a park, not crowded into a tangled canopy. If you walked through it, you would see ferns covering the forest floor and massive conifers rising overhead, relatives of the Araucaria, the monkey puzzle tree. The vegetation was split almost evenly, half ferns, half flowering plants, but the conifers defined the structure. They were slow-growing, wind-pollinated, and built to last. Flowering plants existed, but they did not dominate. The legume family was virtually absent. Today, legumes, beans, peas, acacias, make up a significant portion of Amazon biodiversity. In the Cretaceous, they were rare. The forest had plenty of greenery, but it was not a jungle. It was an open woodland. The canopy did not close. Light was abundant everywhere. This raises a question. If flowering plants had already evolved, if the climate was warm and wet, why didn't they take over? Why did the forest stay open for tens of millions of years? The answer involves two forces, biology and physics. Conifers held the canopy through sheer endurance. Flowering plants grew faster, but something kept them in check. That something weighed several tons and walked on four legs. The paradox is deeper than it first appears. Flowering plants, angiosperms, had been around since the early Cretaceous, perhaps 140 million years ago. They had advantages: faster reproduction, more efficient water transport, and partnerships with insect pollinators. Yet for 70 million years, they could not break the conifer's grip on the tropical canopy. The stalemate was not accidental, it was enforced. Titanosaurian sauropods moved through the Cretaceous Amazon in herds. These were not the largest sauropods that ever lived, but they were still massive, long-necked herbivores that browsed high vegetation and trampled everything else. They knocked over saplings. They stripped low-hanging branches. They turned dense thickets into clearings just by walking through them. Other megaherbivores contributed to the same effect. Together, they kept the forest open. This was not destruction. It was ecosystem engineering. Modern elephants do the same thing in Africa. They push over acacia trees, preventing woodland from becoming a closed forest. The result is a savanna, a mix of grass and scattered trees, maintained by disturbance. Remove the elephants, and the trees take over. The Cretaceous Amazon worked the same way. Dinosaurs were not passive inhabitants. They were architects. Their constant movement and feeding prevented the canopy from closing. Flowering plants had an advantage in growth speed. They could sprout quickly, produce seeds faster, and reproduce more efficiently than conifers. But speed didn't matter if a titanosaur trampled your seedlings every few years. The conifers, slower but more resilient, could survive the disturbance. They had thick bark, deep roots, and the ability to resprout from damaged trunks. They held the upper canopy. The angiosperms stayed below, waiting. The equilibrium was also maintained by resource limitation. Nitrogen availability in the Cretaceous tropics was relatively low. Conifers, with their slow growth rates, could function on less nitrogen. Angiosperms, which grow quickly and produce large amounts of biomass in short periods, need more. Without sufficient nitrogen in the soil, their growth advantage was blunted. The system was locked. This was a stalemate. It lasted for roughly 70 million years. Conifers dominated the architecture. Angiosperms grew in the gaps. Dinosaurs kept the system open. The equilibrium was stable not because it was perfect, but because multiple forces reinforced it. Then an asteroid hit the Yucatan Peninsula, and every one of those reinforcing forces collapsed at once. The Chicxulub impact vaporized rock, ejected trillions of tons of debris into the atmosphere, and triggered a global cascade of fire, darkness, and chemical disruption. The immediate kill rate for plants in the tropics was 45%. It took 6 million years for diversity to return to pre-impact levels. But the extinction was not random. It was selective. Conifers were decimated. They are slow growing. They rely on wind pollination, which fails when the air is thick with ash and the atmosphere is choked with particulates. They need steady sunlight and stable conditions. The impact of winter, a prolonged period of darkness caused by atmospheric dust, shut down photosynthesis. Conifers, which invest heavily in long-term structural growth, could not recover quickly. Many lineages vanished from the tropical lowlands. They never returned as dominants. That was the first blow, the physical destruction of the plants that had held the canopy for millions of years. The second blow was the removal of the ecosystem engineers. Dinosaurs went extinct. The megaherbivores that had kept the forest open disappeared. For the first time in 70 million years, there was nothing to trample the saplings, nothing to knock over the fast-growing trees, nothing to maintain the gaps. The physical constraint was lifted. The third blow was different. It was not destruction, it was an addition. The impact pulverized the continental crust and rained a global layer of ejecta across the surface. Analysis of the KPG boundary layer, the thin band of sediment marking the extinction event, shows a massive spike in iron and other micronutrients. The ash acted as fertilizer. At the same time, the sudden death of the Cretaceous biomass added an enormous pulse of organic matter to the soil. Dead plants, dead animals, decomposing tissue, all of it cycled back into the earth as nutrients. But minerals alone do not fuel rapid forest growth. Plants also need nitrogen to build proteins, enzymes, and chlorophyll. The Cretaceous Amazon had been nitrogen limited. The ash deposition did not directly solve that problem. What solved it was a family of plants that had been waiting in the wings for 70 million years. The forest was gone. The soil was enriched with minerals, but still nitrogen poor. The megaherbivores were dead. The stage was reset, and a new competitive dynamic began. But the transformation required one more ingredient. Mineral-rich ash is useful, but plants cannot build biomass from minerals alone. They need nitrogen. Nitrogen is a limiting factor in tropical forests. It is abundant in the atmosphere. 78% of the air is nitrogen gas, but most plants cannot use it in that form. They need it fixed into compounds like ammonia or nitrate. Before the extinction, nitrogen availability in the Amazon was relatively low. After the extinction, something changed. Molecular clock evidence shows that the legume family diversified explosively in the immediate aftermath of the impact. Legumes have a symbiotic relationship with bacteria called rhizobia, which colonize their root nodules and convert atmospheric nitrogen into usable forms. This is nitrogen fixation. It is a biological superpower. Legumes do not depend on soil nitrogen. They make their own. The post-impact soil was rich in minerals but depleted in bioavailable nitrogen. Legumes filled that gap. As they spread, they pumped nitrogen into the soil, creating a positive feedback loop. More nitrogen meant faster growth for all plants. Faster growth meant more biomass. More biomass meant more competition. The soil transformation was not just about ash. It was about unlocking the growth potential that the ash represented. Legumes were the key. The mechanism works like this. Rhizobia bacteria in legume roots take nitrogen gas from air pockets in the soil and convert it through a series of enzymatic reactions into ammonia. The plant uses the ammonia to build amino acids and proteins. When the plant dies or sheds leaves, that nitrogen enters the soil as organic matter. Other plants can then access it. A forest dominated by legumes effectively fertilizes itself. This does not mean legumes caused the rainforest to exist. It means they provided the chemical fuel that allowed the transformation to happen quickly. Without nitrogen fixation, the recovery might have taken much longer. With it, the forest could rebuild at speed. And speed mattered because the race for the canopy was about to begin. The question is why legumes exploded in diversity after the extinction and not before. The answer likely involves both opportunity and necessity. Before the impact, the open canopy and disturbance regime favored slow, resilient plants. After the impact, the devastated landscape favored anything that could colonize quickly and grow in poor soil. Legumes could do both. They spread rapidly, fixed nitrogen, and in doing so, changed the soil chemistry for everything that came after them. Flowering plants have a structural advantage over conifers. It is visible at the microscopic level. Leaf vein density, The length of veins per unit area of leaf surface can be measured in millimeters of vein per square millimeter of leaf. Cretaceous conifers and ferns had low vein density, around 2 millimeters per square millimeter. Modern angiosperms have vein densities between 8 and 25. More veins mean more water delivery. Water moves through veins to replace what is lost through stomata, the tiny pores on leaf surfaces that open to take in carbon dioxide. If a plant can deliver water quickly, it can keep its stomata open longer, even when conditions are hot or dry. More open stomata means more carbon dioxide intake. More carbon dioxide means faster photosynthesis. Faster photosynthesis means faster growth. Conifers are hydraulically limited. They cannot pump water as efficiently as angiosperms. This makes them slower. In a stable system where growth rate does not matter, where space is plentiful and disturbance resets the clock regularly, conifers can survive. But in a post-extinction scramble, where the survivors are racing to fill empty niches and claim the canopy, speed is everything. The vein density difference is not subtle. A high vein density allows angiosperms to function more like a high-pressure hydraulic system. They can pull water from the soil faster and push it to the leaves more efficiently. This is especially important in the tropics, where temperatures are high and evaporation rates are extreme. Plants that cannot keep up with water loss have to close their stomata, which shuts down photosynthesis. Angiosperms could keep their stomata open and keep growing. Angiosperms grew faster. Without dinosaurs to knock them down, they kept growing. The fastest growers reached the top first. Once they claimed the upper canopy, they began to spread laterally. Branches extended. Leaves overlapped. The canopy started to close. For the first time in the history of the Amazon basin, the forest floor went dark. The closure was not immediate. It took time, perhaps hundreds of thousands of years, for the canopy to fully close. But once it started, the process was self-reinforcing. Taller trees shaded shorter ones. Shade-intolerant species died out. Shade-tolerant species spread. The survivors were not a random sample. They were the species that could either tolerate low light or grow fast enough to escape it. This filtering process accelerated the dominance of angiosperms. A closed canopy changes the rules. In an open forest, light is abundant. Plants compete for space, water, and nutrients, but they do not starve for sunlight. In a closed forest, light becomes the limiting resource. The canopy absorbs most of it. The understory gets what is left, usually less than 2% of the light that hits the top of the canopy. This is not enough for many plants to survive. Conifers, already weakened by extinction, could not compete in low light. They need full sun to grow. Angiosperms, by contrast, evolved shade tolerance. Some species adapted to survive in the dim understory. Others evolved climbing strategies, vines, lianas, epiphytes, that allowed them to bypass the understory entirely and reach the canopy without building thick trunks. The closed canopy did not just block light, it created new ecological niches. Vertical stratification emerged. The forest split into layers. The dark understory, where only shade-tolerant plants survived. The midstory, where smaller trees competed for gaps in the canopy. The main canopy, where the dominant trees spread their crowns. And the emergent layer, where the tallest individuals rose above the rest. Each layer had different light conditions, different microclimates, and different competitive pressures. This layering drove diversification. Plants evolved to exploit specific niches. The darkness itself became an evolutionary engine. The understory layer receives so little light that only plants with extremely efficient photosynthetic machinery can survive there. Many understory species have large, dark green leaves to maximize light capture. They grow slowly, waiting for a gap to open in the canopy above. When a large tree falls, it creates a light gap. Suddenly, the understory is flooded with sunlight. The waiting plants race upward. The gap closes. The cycle repeats. Epiphytes, plants that grow on other plants, exploited a different strategy. Instead of competing for space on the forest floor, they germinate on tree branches in the canopy, where light is abundant. They get nutrients from rain, dust, and decaying organic matter that collects in the bark. Orchids, bromeliads, and ferns became epiphytes. This strategy was only possible in a closed canopy forest, where the upper branches were stable and humid enough to support non-rooted plants. Lianas, woody vines, used yet another strategy. They germinate on the ground but use the trunks of other trees as scaffolding. They climb toward the light without investing energy in thick, supportive trunks. Once they reach the canopy, they spread laterally, sometimes smothering the very trees that supported them. Lianas are now a significant component of tropical forests, but they are rare in conifer-dominated systems. They thrive in closed canopies. The Cretaceous forest was horizontally diverse but structurally simple. The Paleocene forest was vertically complex. That complexity created the conditions for the extraordinary biodiversity we see today. But this is a reconstruction based on fossils and inference. How do we know the canopy actually closed 66 million years ago? Carbon comes in two stable isotopes, carbon-12 and carbon-13. Plants take in carbon dioxide during photosynthesis, and they preferentially absorb the lighter isotope, carbon-12. This means plant tissue is slightly depleted in carbon-13 compared to atmospheric CO2. The degree of depletion can be measured. It leaves a signature in the chemical structure of ancient leaf waxes, which fossilize and preserve that ratio for millions of years. In a forest with an open canopy, air circulates freely. The carbon dioxide that plants absorb comes directly from the atmosphere. Its isotopic ratio is standard. In a forest with a closed canopy, the air near the ground is stagnant. Dead leaves rot on the forest floor, releasing CO2 that is already depleted in carbon-13. Understory plants rebreathe this recycled CO2. Their tissues become even more depleted in carbon-13. This is called the canopy effect. Leaf wax fossils from before the K-PG impact show standard carbon isotope ratios. Leaf wax fossils from after the impact show a sharp drop in carbon-13. This is the chemical fingerprint of a closed canopy. It proves that the canopy closed in the Paleocene, not before. The isotopic signature is unambiguous. The canopy effect is measurable in modern rainforests. Scientists can sample leaves from the forest floor and leaves from the canopy and compare their carbon isotope ratios. The understory leaves are consistently more depleted in carbon-13. This is because the CO2 near the ground is recycled many times before it escapes the forest. Each cycle of photosynthesis and respiration preferentially removes carbon-12, leaving behind CO2 that is progressively enriched in carbon-13 relative to the starting material. But the process also produces organic matter that, when it decomposes, releases CO2 depleted in carbon-13. The net effect in the understory is depletion. The same signature appears in the fossil record. Researchers extract waxy compounds called lipids from ancient leaves. These lipids preserve the carbon isotope ratio from the time the leaf was alive. By comparing lipids from leaves that lived before the extinction with lipids from leaves that lived after, scientists can track the change in forest structure. The shift is clear. Before the impact, no canopy effect. After the impact, strong canopy effect. The canopy closed. There is also direct evidence from plant fossils. Monica Carvalho and her team analyzed over 50,000 pollen grains and 6,000 leaf fossils from Colombia's Bogota Formation, which spans the extinction boundary. The fossils show a dramatic shift in plant composition. Before the impact, conifers and ferns dominated. After the impact, flowering plants took over. The transition happened within 6 million years, a blink in geological terms. The pollen data also show a collapse in diversity immediately after the impact, followed by a gradual recovery. But the recovery did not restore the old system. It produced a new one. The species that returned were not the same species that had been there before. Flowering plants, which had been co-dominant with ferns, became overwhelmingly dominant. Legumes, which had been virtually absent, became common. The leaf fossils tell a complementary story. Before the extinction, most leaves were simple and had low vein density. After the extinction, leaves became more complex and vein density increased. This matches the hydraulic shift from conifer-dominated to angiosperm-dominated vegetation. The physical evidence and the chemical evidence align. The modern Amazon replaced the Cretaceous Amazon. It did not evolve from it. The Amazon rainforest is 66 million years old. Before the KPG extinction, the same region held a different ecosystem with different rules, different dominant species, and a completely different structure. The modern jungle is not a primordial relic. It is a relatively young system built on the ruins of an older one. The catastrophe that ended the Cretaceous was not an interruption of the forest's history. It was the event that created the forest. This challenges the idea of the Amazon as an ancient, unchanging Eden. Ecosystems are not permanent. They are dynamic. They shift in response to disturbance, competition, climate, and the availability of resources. The Amazon is not fragile because it is old. It is contingent because it is young. It exists in its current form because a specific set of conditions, asteroid impact, dinosaur extinction, nutrient pulse, legume diversification, angiosperm hydraulic advantage, aligned 66 million years ago. Remove those conditions and the system shifts. The transformation was not gradual. It was catastrophic, then rapid. The extinction happened over months to years. The recovery took 6 million years, but the new forest was structurally different from the old one within the first million years. The canopy closed. The legumes spread. The angiosperms won. The system flipped to a new stable state. It has stayed there ever since. We are currently removing ecosystem engineers from tropical forests. Elephants are disappearing from Africa. Large primates are declining in the Amazon. At the same time, deforestation is opening the canopy in ways that echo the Cretaceous structure. Climate change is pushing the region toward drier conditions, which favor fire-adapted vegetation over closed canopy rainforest. The parallels are uncomfortable. The Cretaceous Amazon was maintained by megaherbivores and the climate. When the megaherbivores vanished and the system was perturbed, the forest flipped to a new state. We do not know if the modern Amazon can flip back. There is evidence that parts of the Amazon are approaching a tipping point. As deforestation opens the canopy, more sunlight reaches the ground. This dries the soil. Dry soil burns more easily. Fire kills trees and opens the canopy further. The feedback loop can push the system toward the savanna. Some models suggest that if deforestation exceeds 20 to 25% of the Amazon's total area, the feedback becomes self-reinforcing. The rainforest could collapse into a dry woodland within decades. This would not be a return to the Cretaceous system. The megaherbivores are gone. The climate is different. But it would be a structural inversion, from closed canopy to open canopy, from high biomass to low biomass, from high diversity to lower diversity. The forest that took 66 million years to build could unravel in a century. The lungs of the Earth started breathing because the tyrants of the Earth stopped. The world's most biodiverse ecosystem is biological scar tissue over a planetary wound. That is not a comforting origin story, but it is the real one. The Amazon is not eternal. It is a product of disaster, built in the shadow of an extinction that killed half the plants in the tropics and reset the competitive balance that had held for 70 million years. The forest we see today is what grew in the aftermath. And history suggests that what grows in the aftermath of one catastrophe can be swept away by the next.